James Chadwick's 1932 publication, Possible Existence of a Neutron Appearing in Nature, stands as a monumental achievement in nuclear physics, marking the discovery of the neutron and reshaping our understanding of atomic structure. This essay will explore the intellectual lineage of Chadwick's work, the experimental methodology he employed, its immediate impact on the scientific community, its subsequent influence on nuclear physics and technology, and the critical reception it received. The story of the neutron's discovery begins well before 1932. The prevailing model of the atom in the early 20th century, spearheaded by Ernest Rutherford and his collaborators, pictured a nucleus containing positively charged protons surrounded by orbiting negatively charged electrons. This model, while successful in explaining many chemical properties, faced a significant challenge. The atomic mass of elements often greatly exceeded that predicted by the number of protons alone. For example, helium possessed an atomic number of 2, suggesting 2 protons, yet its atomic mass was approximately 4. This discrepancy led Rutherford to postulate, as early as 1920, the existence of a neutral particle within the nucleus, a particle he tentatively termed the neutron. This hypothetical particle, possessing a mass comparable to the proton, would account for the missing mass and resolve the inconsistencies between atomic number and atomic mass. Rutherford even considered the neutron to potentially be a proton and an electron bound together in a peculiar. Several researchers attempted to find evidence of the neutron during the 1990s. However, the neutral nature of the particle presented an enormous experimental hurdle. Charged particles, such as protons and electrons, readily interact with matter through electromagnetic forces, allowing for their detection using ionization techniques. A neutral particle, however, would interact far more weakly, requiring a more subtle and indirect approach for its detection. One particularly relevant investigation came from Walter Bothe and Herbert Becker in 1930. They observed that when beryllium was bombarded with alpha particles, a highly penetrating, electrically neutral radiation was emitted. Initially, they interpreted this radiation as high-energy gamma. Ian Joliot-Curie and Frédéric Joliot, in Paris, further investigated this phenomenon. In 1942, they found that this radiation, when directed onto paraffin wax, was able to eject protons with energies far exceeding those that would be imparted by gamma rays of similar penetrating power. The Joliot-Curies attempted to explain their results while invoking a Compton scattering process involving extremely high-energy gamma rays. However, calculations based on the laws of conservation of energy and momentum reveal significant inconsistencies with this interpretation. The energy of the hypothetical gamma rays required to produce the observed proton energies would have had to be implausibly high, rendering the Compton scattering explanation untenable. There remained lingering ambiguity regarding the true nature of the radiation. James Chadwick, at the Cavendish Laboratory in Cambridge, carefully examined the experimental data obtained by Bothe and Becker and the Joliot-Curies. Chadwick possessed an acute understanding of nuclear physics and a mastery of experimental techniques. He recognized that the Joliot-Curies' observations could be elegantly explained by the existence of a neutral particle with a mass approximately equal to that of the proton, the very neutron that Rutherford had predicted. Chadwick's crucial contribution lay in designing and performing experiments that definitively established the nature of the radiation. He meticulously measured the energies of protons and other light nuclei, such as nitrogen, ejected by the radiation emanating from beryllium bombarded with alpha particles. He then applied the laws of conservation of energy and momentum to these collisions. His analysis demonstrated that the experimental data could be consistently explained by assuming that the radiation consisted of neutral particles having a mass very similar to that of the proton. Had the radiation been high-energy photons as previously theorized, the conservation of momentum and energy would be violated. Chadwick's experimental setup involved bombarding a beryllium target with alpha particles emitted from a polonium source. The resulting neutral radiation was then directed onto targets containing various light elements, such as hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, and argon. He then measured the recoil energies of the nuclei of these elements using an ionization chamber connected to an amplifier and an oscilloscope. By comparing the recoil energies of different nuclei, Chadwick was able to accurately determine the mass of the neutral particle. He calculated the mass of the neutron to be between 1.005 and 1.008 atomic mass units. These measurements provided conclusive evidence that the neutral radiation consisted of particles with a mass comparable to the proton, thereby confirming the existence of the neutron. The title of Chadwick's Nature paper, Possible Existence of a Neutron, appears unstated in retrospect given his profound discovery. The discovery of the neutron had an immediate and profound impact on the scientific community. It provided the missing piece needed to complete the picture of atomic structure. The nucleus, it was now clear, consisted of protons and neutrons, collectively referred to as nucleons. The number of protons determined the element's atomic number and its chemical properties, while the number of neutrons accounted for the isotopes of each element. Atoms with the same number of protons but different numbers of neutrons. This understanding resolved the long-standing puzzle of atomic masses and provided a more cohesive framework for understanding the periodic table. Physicists rapidly integrated the neutron into nuclear models. Werner Heisenberg, soon after Chadwick's announcement, developed the proton-neutron model of the nucleus. This model depicted nuclei as bound states of protons and neutrons interacting through a strong, short-range force, a force quite distinct from the electromagnetic force. This model served as a foundation for all subsequent nuclear physics research. The discovery of the neutron also opened up entirely new avenues of research in nuclear physics. Enrico Fermi and his group in Rome quickly realized that neutrons, lacking electric charge, could easily penetrate atomic nuclei, even those with high atomic numbers. In 1934, Fermi began a systematic study of neutron-induced radioactivity, bombarding various elements with neutrons and observing the resulting radioactive isotopes. These experiments led to the discovery of numerous new radioactive isotopes and paved the way for the development of nuclear fission and nuclear reactors. Crucially, neutron-induced fission of uranium, discovered by Otto Hahn and Fritz Strassmann in 1938, and explained by Lise Meitner and Otto Robert Frisch, relied directly on the existence of neutrons. The fission process releases more neutrons, allowing for a self-sustaining chain reaction, the basis for nuclear power and nuclear weapons. The applications of neutron physics expanded rapidly. Neutron scattering became a powerful tool for probing the structure of materials at the atomic level. Neutron activation analysis allowed for the precise determination of trace elements in various samples. Neutron radiography provided a non-destructive method for inspecting the interiors of objects. These techniques found applications in diverse fields, from materials science and engineering to medicine and archaeology. The development of nuclear reactors and nuclear weapons during World War II dramatically illustrated the practical importance of Chadwick's discovery. The Manhattan Project, the massive Allied effort to develop the atomic bomb, depended critically on the understanding and control of neutron-induced nuclear reactions. The first controlled nuclear chain reaction, achieved by Fermi at the University of Chicago in 1942, was a direct consequence of the knowledge gained through Chadwick's work. The use of atomic bombs on Hiroshima and Nagasaki demonstrated the devastating power of nuclear energy, forever altering the course of history. The reception of Chadwick's discovery was overwhelmingly positive within the scientific community. His careful experiments and rigorous analysis left little room for doubt. However, the Joliet-Currys, who had come so close to discovering the neutron themselves, felt some degree of disappointment. Their initial interpretation of their experimental results as Compton scattering of high-energy gamma rays prevented them from recognizing the true nature of the radiation. Nevertheless, they later acknowledged Chadwick's priority and the significance of his work. After all, scientific progress builds incrementally, with each new discovery relying on the foundations laid by previous research. Chadwick received the Nobel Prize in Physics in 1935 for his discovery of the neutron. He went on to play a crucial role in the British atomic bomb project during World War II and later served as Master of Gonville and Caius College, Cambridge. The legacy of Chadwick's discovery continues to resonate today. Neutron physics remains a vibrant and active field of research, with applications ranging from fundamental studies of nuclear structure to the development of new energy sources and medical treatments. Advanced neutron sources, such as spallation neutron sources and research reactors, provide intense beams of neutrons for a wide range of experiments. Chadwick's 1932 paper represents a watershed moment in physics, fundamentally changing our understanding of matter and opening up a new era of nuclear science and technology. His meticulous experimental work, coupled with his insightful interpretation of existing data, established the existence of the neutron and paved the way for countless subsequent discoveries and innovations. The neutron, once a mere theoretical construct, became a cornerstone of our understanding of the universe and a powerful tool for exploring its secrets. The lasting impact of Chadwick's discovery serves as a testament to the power of scientific curiosity, rigorous experimentation, and insightful analysis. His contribution exemplifies the quest to understand the fundamental building blocks of nature.